जो है समाज से ये बहिष्कृत किया जा रहा है, बिकॉज एनर्जी ये कंज्यूम करता है। लेकिन इसके पीछे जो काफ़ी रिसर्च हुआ, कितना एक्सपेरिमेंट्स किए गए, थॉमस अल्वा एडिसन साहब ने बहुत सारा एक्सपेरिमेंट किया, रिसर्च किया, तब ये कहीं पहली बार किसी के घर पे बल्ब आया था। लेकिन चूँकि पावर कंजप्शन इसका बहुत अधिक है, बहुत हाई है, तो उसकी जगह पे इसको कम यूज़ कर रहे हैं, तो ये विलुप्त प्राणी हो रहा है। इसका हम लोग जरा रेजिस्टेंस मेजर करेंगे आज, ठीक है। तो इस पर क्या क्या लिखा है, कौन सी कंपनी है, सूर्या कंपनी, 100 वॉट इस पे लिखा हुआ है, और 230 वोल्ट है ना। तो जरा इसका रेजिस्टेंस मेजर कर सकते हैं, कैलकुलेशन कर सकते हैं कितना होगा। पावर इज 100 वॉट एंड वोल्टेज जो है वो लिखा है 230 वोल्ट। तो कितना रेजिस्टेंस होगा इसका, हाँ जरा कैलकुलेट कर सकते, 5 कितना आना चाहिए, अराउंड कितना होना चाहिए।
V square upon power is V square upon R. Yeah. Okay.
ठीक है, तो कितना अराउंड आना चाहिए इसका, 5
29
सभी का यही आ रहा है, ठीक है। तो इसको हम मेजर कर सकते हैं थ्रू दिस मल्टीमीटर, है ना। ये मल्टीमीटर है और इसको रेजिस्टेंस मोड पे लगाएंगे और 529 आ रहा है, तो हम इसको कहाँ पे लगाना चाहिए, 20K पे आसपास लगा लेंगे, ठीक है। 2K पे लगा लेते हैं, 2K पे आप मेजर करिए, हम पकड़ लेते हैं, इधर आपको देखिए।
किलो ओम, किलो ओम।
और इसकी रेंज चेंज कर देते हैं, अब मेजर करिए, 200 पे किलो ओम पे 40 ठीक है। और कोई मेजर करेगा,
So what is the expected temperature? What is the expected temperature? Okay. And what is the order of your alpha temperature coefficient? तो कैसे मेजर करोगे? फिलामेंट पर कहाँ ले जाओगे?
फिलामेंट भी लगाएंगे ना, उसकी ऊपर सतह में लगाएंगे।
वो तो बहुत कम आएगा, वो तो बहुत कम आएगा। फिलामेंट का टेम्परेचर बहुत हाई होता है।
फिलामेंट,
हाँ, बल्ब का टेम्परेचर बहुत कम होगा, शीशे का टेम्परेचर बहुत
शीशे
कम।
का जो टेम्परेचर होता है, तो इवन आप नॉर्मली
उसको तो नाप सकते हो, उसको नाप सकते हो, कितना होगा? 200-300 डिग्री होगा।
200-300 डिग्री अंदर का नहीं कर पाएंगे।
हाँ, फिलामेंट का नहीं कर पाओगे।
बल्ब तोड़ देने के बाद भी तो फिलामेंट रहता है।
क्या चीज़? अच्छा, इससे निकाल रहे हो 0.38 क्या पर के? अच्छा, देखो वो है तुम्हारा डेटा कनेक्शन है? नेटवर्क नहीं है, नेटवर्क नहीं है, वाईफाई नहीं है, लगा दो।
अच्छा, वो पासवर्ड
क्या हुआ? इतने सारे लोगों को दिखाया, कुछ बोला नहीं तुमने?
रीडिंग ले रहे हैं। कितना कितना रीडिंग आया? 38.6 ओम। इधर किसी का कुछ इंक्रीज किया रीडिंग? 38.6 100 के अबव नहीं किया, 38 पॉइंट और 40 के अराउंड। आपका भी 40 के अराउंड। तो जो रीडिंग है वो आ रही है मल्टीमीटर के थ्रू 40 ओम समथिंग, ठीक है। और जो हमने कैलकुलेट की है वो रीडिंग आ रही है 529 ओम। तो ये इतना डिफरेंस क्यों आ रहा है? व्हाट इज द प्रॉब्लम? इतना इतना डिफरेंस?
कंपनी खराब है।
कंपनी सूर्या ठीक नहीं है, इसीलिए हम लोग रिजेक्ट भी कर रहे हैं। ऐसा हो रहा है क्या?
ये क्या है? हाँ, अच्छा।
हाँ, तो ठीक है, ज्यादा पावर कंज्यूम करता है इस वजह से, लेकिन वो रेजिस्टेंस में डिफरेंस क्यों आ रहा है? क्यों डिफरेंस क्यों दिख रहा है रेजिस्टेंस में? हाँ? अच्छा,
टेम्परेचर।
अच्छा, एक बात इधर से आई कि अगर टेम्परेचर इंक्रीज करेगा तो रेजिस्टेंस ऑल्सो इंक्रीजेस, है ना? बहुत स्मॉल टाइम के लिए, तो थोड़ा टाइम और देना चाहिए। और कोई कुछ आंसर करेगा? कर सकते हैं, लेकिन यहाँ पे अभी वो अरेंजमेंट से नहीं।
नहीं, मुश्किल है। कैसे करो, कैसे करोगे? You have to design the bulb because we need a thermocouple inside at the filament, and that we cannot put. So you have to redesign the bulb so that a thermocouple can be put there. रेसिस्टेंस मेजर थोड़ी करते हैं, पावर मेजर करते हैं ना। See the temperature coefficient, temperature coefficient of this resistivity for tungsten is 5.6 into 10 power minus 8 ohm meter. लिखना। Wait. No, this is resistivity. Wait. This is resistivity. Table of resistivity and temperature coefficient. Temperature coefficient per degree Celsius, right? And I need tungsten. Where is tungsten? Tungsten, right? Tungsten is 0.0045 per degree Celsius, right? Okay. So now can you calculate the temperature of filament? Because we don't know the temperature of filament. The resistance at this room temperature is 40 ohms, and at that temperature where it glows, when we apply 230 volts, the company says that it does give me 100 watt, right. So the resistance must go 529 ohm. So with this information, can we calculate the temperature of the filament? Do it. You have R resistance at temperature T, resistance at temperature some 0, not necessarily 0 Kelvin or so, any reference, 1 plus alpha and then T. Correct. So now you know your what is R naught? How much is R naught? 40 ohm. And what is this RT? 529, and then alpha is here. So you can get the temperature. How much it is? $2716. Okay, he is telling 2716. No, we will take the difference from here. Difference from the room temperature. So the T you get is the difference from this room temperature at some temperature, or you can say that this is at some temperature T naught and this is T minus T naught. One more confirmation to this number 2716 is there. So the filament temperature would be 2700 plus room temperature, which may be 20 or so, around 3000, no, not 3000, yeah, 2700 something. Now why this only gives a rough estimate? I have taken alpha value for tungsten from a reliable site. The two resistances are well known, 40 ohms we have just measured, and if it does give 100 watt at 230 volt, the resistance has to be 529 ohm. So why do I say that this temperature 2700 is only a rough estimate for this filament temperature? This equation is not valid for a big range of temperature. This is around 20 degrees Celsius, is around room temperature. The alpha value which is quoted in the textbooks is for around room temperature values, around 20 degrees. In fact, they write at the table that 20 degrees Celsius. So only there it is this. In this full range, alpha will have a non-linear behavior, and therefore it only gives me an estimate. What is the temperature of the surface of the sun from where we are getting all this light? And that light is white light, okay, right. So the color of light can also give you an estimate of the temperature from which it is emitted, okay. So 2700 is fine. The spectral analysis if you do of sunlight and the light coming from bulb, they will be different. The peak wavelength will, peak intensity will be at some other wavelength, not the same, but the order is okay, order is all right, fine. The light that you are getting from these tube lights, that is also something like white light, some bluish, but still you are getting visible light. So, what is the temperature of this tube? That is not 2700. Why Wien's law is not applicable here? That is called black body radiation. Tube light is not black body radiation, but filament bulb is tube light, is black body radiation. For this filament bulb, I am saying that since I am getting that white light, the temperature of the filament must be around 2700 or 3000 Celsius or Kelvin. But the tube light is not giving me, is also giving me white light, but I am not able to expect, I should not expect that the temperature of the tube light inside, outside, anywhere is anywhere close to 1000 degrees Celsius or so. A glowing tube light you can very easily handle.
According to the Wien's law, at a lower temperature, we can obtain the wavelength in the visual region, but corresponding to that intensity will be low. If I am going to decrease the temperature, sir, then the shift will be something like this. It means wavelength is also going to shift, and intensity is going to decrease. Intensity of this radiation is less compared to the.
So, what you are saying is that although the temperature is small, the peak intensity is at some bigger, much bigger wavelength, but then there is a tail of the distribution in the visible region also, and it is that tail that we are seeing. The light that is coming from here is coming because of that tail. See, let me explain what he is saying. So, if you have lambda in intensity, okay, and then the radiation pattern is something of this kind, and this is that lambda m, and that depends on temperature. Lambda m into T is some 0.028 something in some units. Okay. So, you increase the temperature, this lambda m decreases, you decrease the temperature, lambda m increases. So, for 5000 Kelvin, we know that this lambda m is visible. So, let us say 600 nanometers Nm. So, that is the kind of thing here. Now, what is the tube light temperature? 100 K, 200 K, 300 K, 400 K, 500 K, which one? You can handle it very well, the glowing one. Okay, so our body temperature is some 37 Celsius or so. So, that outer part of the tube is at that temperature 40, 50, 45 Celsius. So, 300, around 300 Kelvin. Okay. So, maybe inner part is slightly more, 500 Kelvin. All right. So, now if it is 500 Kelvin, instead of 5000, now it has become 500. So, where does this go? This goes to 6000 nanometer. Okay. So, the peak occurs at 6000 nanometers. But he says that okay, fine, but it goes down, 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 but even at that 600 nanometer, this 6000, then 1000, if I do 5 parts, so it will be somewhere here. So, but this small intensity here is that what we are using in this room. How inefficient is this? We are wasting this whole energy and using this tiny part of the spectrum. How inefficient this tube light will be? And people say that don't use filament bulb, better use tube light at least, then CFL and then LED and all that. But if you compare from filament bulb, tube light is definitely advisable. What is wrong?
Sir, inside inside the plasma, what is the temperature of that?
Not much. The temperature is not much.
So maybe for that temperature, the atoms are accelerated so much that they start emitting photons. इतना ज़्यादा temperature required ही नहीं होता उसके बाद. Because the phenomena is just.
This is not radiation. It's not radiation. See, this black body radiation is you have a hot body, and because of the temperature it is radiating. Okay. In a tube light or in a CFL, the mechanism is very different. You have that vapors, and then you apply some electric field there, and there is some accelerations of the electrons, and then those electrons go to make collisions with the other ions. They go to some excited state that comes down and then emits light. What kind of light is emitted inside, you know that tube light? What range of wavelength? In a tube light or in a CFL, ultraviolet is emitted. So ultraviolet means less than the visible. Okay, so that's the range in which the light is emitted, not this range, not this range. Inside this tube light, the light is emitted in ultraviolets. And why this ultraviolet? Not because of the temperatures, but because of those energy levels. Because of those energy levels, the energy levels are such that when this electron hits and it goes, it takes some energy from there, goes to excited state, comes down, then the wavelength falls in ultraviolet region. And then how come we are getting this visible light and we don't apply any sun cream and all those things to protect ourselves from the ultraviolet? Right. This coating, this fluorescence coating is such that when ultraviolet falls on that, it absorbs the ultraviolet and emits visible. That is how we get this visible light. Okay. Temperature would be all of this order only. The temperatures are not very high. The temperatures are not very high. It's that mechanism is totally different. This emission is not because of temperature. This Wien's law and this distribution, Planck's distribution, all this is for temperature, radiation coming out because of the temperature. Here the radiation is coming out because you are pumping the ions to go to some excited state, and from there it de-excites and then gives you a particular hydrogen tube, for example. You might have used in your labs. Did you use those sources, or the discharge tubes they are called? You have a thin tube in which hydrogen or neon or some other gas is there, and then apply electric field connected to voltage, and then it glows, and then you from the spectrometer you see what is the where those lines are coming. So all those things are at very nominal temperatures, right? So this doesn't apply to that. That mechanism is totally different. Yeah. But filament bulb, yes, this radiation that we are getting is because of the temperature. That is why it closely follows that.
I have one hollow rod.
Pipe.
Hollow pipe. Okay. So I need one
Volunteer. The age old experiment, everyone knows. आप इधर आओ, उधर दिख नहीं रहा है.
I am dropping some objects. You can count how much time it takes.
Count as 1, 2, 3.
Start, I think you can use your mobile phone also.
If you can.
If you can. Otherwise, और लोग कर लेंगे. आप इसको सीधा होल्ड रखिए. Okay. Yes. How much time? Okay. आगे
when you see that he has left the object, you have to start the stopwatch. When you see the things coming out, you have to stop the stopwatch. See, you have to look at the object and then you have to look at your mobile to put it on. Bigger one.
Bigger one. Okay.
Point? 0.15.
0.15. Okay.
This 0.14. Good.
Okay, now I have another object, small.
दिखाई तो दो.
अब निकला है. पहले वाले टाइम सब सही नहीं थे, आप बस ऑन ऑफ करते हैं. वो आपका रिएक्शन टाइम है कि आप कितनी जल्दी ऑन ऑफ कर रहे हैं. ओके, अगेन. यस.
1.8 second.
So what is this? Magnets or magnet?
Each magnet has so many tiny magnets inside.
1.92. तो ये काफी टाइम लेता है और ये अट्रैक्ट नहीं कर रहा है. ये क्या चीज है? सभी लोग पहचानते हैं. कॉपर. ठीक है. और ये मैग्नेट से अट्रैक्ट नहीं होता है. ठीक है.
So why does it slow down? Everyone knows that, of course. Why does it slow down? Huh? Eddy currents. Eddy currents are produced.
Okay. So now I have.
Now this is the real quiz.
अभी हमने कॉपर रॉड या ट्यूब लिया था. अब ये कॉपर
Wire.
वायर्स हैं करके और एक सोलेनोइड क्रिएट किया है. इसका एक ये पार्ट है और इसका ये सेकंड पार्ट है. अभी बोथ पार्ट इज ओपन.
And it is enameled. It is enameled, insulating, so you cannot have any conduction between the turns. It has to go round the whole thing.
तो हमने वही उसी तरह का रॉड बनाने का कोशिश किया है. ओके रंजीत.
नहीं रुको रुको पहले पूछो.
हाँ.
If I drop the magnet, what will happen? Will it slow down? If I drop the magnet in this tube, will it slow down? Will it take 1.8 seconds or it will take 0.18 seconds? हाँ? क्या होगा? Quickly आएगा. Quickly आएगा 0.18 second. Why? Because of the. Okay. What do you think? Slowly आएगा. Why? सोलिनॉइड जैसा बिहेव करेगा. एक्सिस के अलॉन्ग इलेक्ट्रिक फील्ड बनेगा. Okay. What will happen? Quick or slow? Slow. वो पता नहीं क्यों इधर का साइड काफी डिवाइडेड रहता है. इधर वाले ज्यादा बोलते हैं स्लो हो रहा है, इधर वाले ज्यादा बोल रहे हैं क्विक. और इधर भी क्विक वाले लोग हैं, ऐसा नहीं कि नहीं है, माइनॉरिटी में.
तो ड्रॉप करते हैं ना.
Okay, what if I connect the two ends? What if I connect the two ends so that the circuit is complete? Slow or fast? Huh? Slow? Slow or fast? Slow down. Now it will slow down. Huh? There is no battery connected.
We are not passing any current, so it's the same situation.
In that tube also there was no battery connected. In that copper tube, when it took 1.8 seconds, we just put a magnet there. There was no battery connected. Slow or fast? Slow or fast? Yeah, we have joined. We have joined the two ends. Previously, we did the experiment with the two ends open. Now we are joining the two ends. Slow or fast? Must be slow. It should slow down. The circuit is complete. The magnet is going. So eddy current should be there. So let's see. Why there was no eddy current this time? When this whole thing is one circuit. Pardon? Single wire. No. The turns are not opposite. Yeah. All the turns are going in the same direction. Even if it is to be repeated, it will be repeated in the same direction. All, if you see from huh? No core. There is no core. Okay. Good, very good. Yes. This is an observation that in a copper tube, you had copper everywhere, right? Here, you do have copper, but then you have some insulating plastic material here, and therefore the current is not able to form. So the current has to form on this surface or this surface. The magnetic field penetrates this plastics. Okay? Yes or no? The magnetic fields, the magnetic, और ये पिन दो पकड़ने वाला, ये है. Give me some any plastic. ये देखो ये plastic है, right? And I have a magnet here. ये magnet है और ये plastic है, और उसके बाद फिर हम ये, हाँ, okay. लगाओ, पीछे लगाओ, इसको हटाओ, हाँ, लगाओ नीचे लगाओ. Okay. So the magnetic fields can penetrate all these plastics, etc. Right? And the current doesn't have to cross through that plastic. It has to go on the copper. Right?
Sir, the electrons in the copper pipe have the full breadth of the copper pipe to flow. इसमें इस डायरेक्शन में अगर इलेक्ट्रॉन का मूवमेंट देखे तो सिर्फ एक वायर का इंजेक्शन है तो उधर वो फ्लो करेगा नहीं. जो इस डायरेक्शन होगा उसका मैग्नेटिक फॉर्म कम होगा.
So what you think is the eddy current flows like this. So the current that flows on this copper tube when magnet is going through inside, most of it is along the length of the tube. That's your guess. And since you in different turns we are not allowing that particular direction of current, that's why the eddy current is negligible. That's your guess. No, it's a good guess. It's definitely a good guess. But then the only thing is that the current should go like this, and that we can argue from our Maxwell's theorem whether it goes like this or it goes like this. That we can argue.
Sir, if it is going in the turns, then only then its magnetic field will lead in the opposite direction. Only then it will oppose. If it is going in this direction, sir, so then how it will oppose the motion of the magnet?
फिर से बोलो.
Sir, when current is going in the circular groups in this direction, only in the direction of the
Okay. He is giving counter arguments, right? See, it's a very good discussion. So let everybody know about that. See, what first guess was, that is how it goes. Science develops. The first guess was, in the solid copper tube, the eddy currents were formed. In the solenoid, they were not formed. So what is the difference? One obvious difference is you have turns, and one turn and next turn is insulated. So current cannot go in the solenoid along the length of the tube, whereas in the tube current go along the length of the tube. Conjecture. Possibly the current goes along the length of the tube, and that is why there the phenomena worked, but here it did not work. Right. So, one has to test whether the eddy currents in that copper tube experiment, whether it goes prominently along the length or along this axial. And then the counter argument is, if it has to oppose the motion of the magnet has some north here and some south here, or south here, north here, but if it has to oppose this motion of the magnet, it has to repel the magnet up. So, magnetic field should be in vertical direction, and to have a field in vertical direction, the current must be circular, not linear. So, that is the counter argument. Good, very good. Yes.
In this case, since the magnet is going down, the magnetic flux in the upper part is going on decreasing, and in the downward direction. So the direction of current in the upper part would be opposite to the downward part. But since this is now connected, those will oppose each other, and because of equal magnitude, the effect will be cancelling the current.
Wonderful. Let me explain what he is saying. See, in the copper tube, in this experiment, when the magnet is here, if you consider the part of the tube just below this magnet, the magnet is approaching the loop. Okay? And if you look at the part just above the magnet is going away from the loop. So, what will be the direction of current induced in the lower part and in the upper part? Will they be in the same direction or in opposite direction? Opposite direction, right? Opposite direction. In case suppose this is north, this is south, and your fields are coming like this from north, and then you have a loop and it's approaching. In other case, you have a loop which is above this and it's going down, but the field is still in the same direction, correct? The field here is in, and field here, both fields are in the same direction. So, the fields are in the same direction, and therefore, your flux का जो क्या कहते हो magnitude, that will remain the same, flux times field times area, positive to positive, negative to negative. एक case में the magnitude is increasing, another case magnitude is decreasing. So, you will have opposite direction of the current. So, when the magnet falls in this copper tube, you have currents here say anti-clockwise, currents here clockwise, and then both of them, this anti-clockwise and this clockwise, both of them repel this magnet up and it slows down. In the tube, this is possible. In the tube, this is possible that you have a current here and a current here, opposite current here. In a solenoid, that is not possible. If your current is clockwise here, it has to be clockwise. The electrons cannot get collected at one place. So, in a solenoid, that is not possible. And therefore, eddy currents are not produced in the solenoid, it is produced in the tube.
Sir, so when the ends of the solenoid were not connected, it shouldn't be different.
Same story, na? Connected or not connected is not important, right? Okay, if it is not connected, then anyway the current cannot go. Even if it is connected and you demand that in half the solenoid it should go this way, half the solenoid it should go that way, it will not. So, in both cases there will not be any current in this, right.
Okay, so I have
वो जंपिंग रिंग कहाँ है? जंपिंग रिंग है नहीं? अच्छा रखिए, ठीक ठीक.
so I have two coils. I am connecting with
This is a kind of a okay magic show.
और ये इसको हमने गैल्वेनोमीटर से कनेक्ट कर दिया. तो हमने क्या किया, मैग्नेट को एक कॉइल से हम पास कराते हैं, इस कॉइल से, और फैराडे लॉ ने फैराडे से जो कहा
वो
था,
पहले वो ठीक से दिखा दो
हाँ
ऑपरेटर्स.
वो दिखाते हैं.
अच्छा ओके.
ठीक है, होगा ना? रिफ्लेक्शन दिख रहा है गैल्वेनोमीटर पे. ठीक है, फैराडे से ने कहा दोनों या तो कॉइल मूव करे या मैग्नेट रिलेटिव मोशन होना चाहिए, तो वही हम कर रहे हैं. ठीक है, ओके. तो ये दो कॉइल जो है वो आपस में सीरीज में कनेक्टेड है गैल्वेनोमीटर के थ्रू, और इसमें जब हम मैग्नेट को ले जाते हैं तो यहाँ पे गैल्वेनोमीटर में रिफ्लेक्शन हमें दिखाई पड़ता है. तो एक बार एक साइड में, एक बार दूसरे साइड में.
वहाँ पे टेबल के साइड में करो एक्सपेरिमेंट और अपने उस साइड में रहो. हाँ यस.
So I am producing कौन सा करंट? अल्टरनेटिंग करंट, है ना? हम बार बार इस मैग्नेट को इसमें जब ले जा रहे हैं तो एक बार जीरो के इधर, एक बार जीरो के इधर, तो वो, और अगर हम इस कॉइल में मैग्नेट को ले जाएं तो देखिए क्या होता है. कोई डिफ्लेक्शन नहीं. यहाँ तो फैराडे साहब का सही है आंसर, लेकिन यहाँ पे कुछ और ये कनेक्ट जो है, कनेक्शन जो है वो सीरीज का, तो उल्टा कनेक्ट करके देखिए, उल्टा कनेक्ट करके देखिए. ओके, ये जो इधर थी वो उधर हो गई है. उस पॉइंट में चला दो, उस पॉइंट में चला दो. कॉइल है, इसमें भी देखिए कॉपर टर्न्स, जितने टर्न्स इधर हैं उतने टर्न्स उधर हैं. क्या हुआ? फ्लक्स चेंज नहीं हो गया. किसी ने कहा फ्लक्स चेंज नहीं हो गया, ऐसा कुछ? सबने पहले कहा था ये मैजिक है, तो
अलग से बने बिल्कुल. कुछ तो है, कुछ तो फर्क तो है. कोयल में ही है जो कुछ है. सेम कोयल उधर ले जाओ, इधर ले जाओ, तो क्या क्या किया होगा कोयल में? ओके ओके गुड.
वही हमने कहा, पहले आंसर आ गया था.
He had already told this earlier. हाँ? Right.
नहीं आंटी.
तो एक बार ऐसा करें, एक बार ऐसा करें. And how can you do that? काउंट करके 1000 बार इधर से, फिर उल्टा 1000 बार उधर से. Very simple way to do that. Very simple way to do that. Take the wire, fold it in two. ऐसा ऐसा बना लो. वायर लंबा लेकर के ना उसका ऐसा फोल्ड. ओके दोनों ओपन एंड छोड़ दो और उधर वाले एंड से वाइंड करना शुरू करो.
तो नेक्स्ट एक्सपेरिमेंट.
नहीं, let everyone understand this. Visibly you won't see any difference, okay, since this is made for entertainment. Since this is made for entertainment, they have took care that visibly there is no difference, right. So in one of the coils it's a normal winding, and another coil it's half the winding are clockwise and half the winding are anti-clockwise, and therefore although continuity is there, resistance is there, so current does flow in that series circuit, everything is there, but then the flux change is 0. On नहीं किया ना? Okay, now this is a little bit more serious experiment. Another solenoid here or coil, and you do have a core here. The core is made of cycle spokes. Cycle spokes are cut and then stuffed into this gap to make this system, and the two open ends of the coil are connected to this plug, so that we can apply 220 volts, and is sturdy enough, it will hold that 220 volts and will not burn. So the first thing is, if I apply that 220 volt and put an aluminum ring over this. This is also a very old famous experiment. What is this experiment? If I apply the 220 volt, what will happen? It will jump. Jumping ring, huh? Okay. So let's enjoy that jumping. Okay, so that you know, why it happens, that also you know. Same story. Since it is AC, so the magnetic field is changing the direction continuously, and therefore there is some eddy current in this ring, correct? Because the magnetic field, you have a coil, this coil, so the current is going this way, this way, this way, this way, this way. So the magnetic field is up, down, up, down, up, down. And so that magnetic field comes here also because of this core, and hence you have current in this clockwise, anti-clockwise, clockwise, anti-clockwise, clockwise, anti-clockwise, and then why should it jump? If the current is there, fine, there is a current, there is a current here, there is a current here. The two currents can repel, two currents can attract. Why should it repel only? When I switch it on, the current increases from 0 to maximum. So whichever direction is the magnetic field, its magnitude increases, flux increases, and therefore the current induced in the ring is opposite to the current which has produced that primary magnetic field. So the currents are in opposite sense, and therefore they repel, and therefore it jumps. That is fine. But then tell me, when it is staying in equilibrium, consider this state, it is staying in equilibrium, okay, switch off, and we have put it on for quite considerable time, say half a minute, 30 seconds or so, and per second 50 times that magnetic field is changing, 50 hertz AC line. So half the time the current is increasing, current in the primary is increasing, but half the time the current is decreasing. It is an AC. And if the current is increasing and the two currents are in opposite direction, magnetic field increasing, flux increasing, then when the AC current drops, the magnitude goes down. and the flux decreases in magnitude, then the current in ring should be in the same direction as current in the primary. Okay. Current induced in this ring will be opposing the cause which has produced it. So, if the increasing magnetic field has produced it, it will be induced in a direction to oppose, to produce an opposite magnetic field. But if the primary magnetic field is decreasing in magnitude, then it has to oppose that decrease. So, it will produce magnetic field in the same direction as the primary field, right. So, for that the current in the ring, this aluminum ring, should be the same as the current in the primary ring, if they have to produce the magnetic field in the same direction. If they have to produce magnetic field in the same direction, if this is anticlockwise, that should also be anticlockwise. So, half the time they are in repelling mode, half the time they are in attractive mode. So, if I take a time average, and remember it is 50 hertz, 50 oscillations per second, right. It is not that the frequency is very low and I am only seeing a part of it which is approximately in the same, no. The average magnetic force on this ring is 0, but the gravity is always there. The average gravitational force is not 0, weight is not 0. How it is in equilibrium?
For the ring we have IL cross B अगर बनाए तो
IL cross B, yeah. Force is IL cross B, yes.
तो B and I जब एक ऐसा डायरेक्शन मान रहे जिसमें ऊपर जा रहा है, दूसरे में B भी वैसी डायरेक्शन में चेंज होता है, I भी वैसी डायरेक्शन में चेंज होता है, तो ये इक्विलिब्रियम मुझे IL cross B को correspond करेगी. मतलब I'm saying कि B भी वैसे चेंज होगा, I भी वैसे चेंज होगा कि IL cross B एक ही डायरेक्शन में है.
Let us work it out. Let us work it out. You have this primary, and suppose the current here is in increasing cycle. The magnetic field produced is in this direction and it is increasing. Correct. Now you have a ring here. So, the current is like this. What is the direction of the current here? This is, if I see from top, this is anti-clockwise. So, it has to be clockwise because your dB dt is positive, the flux is, so the current should be in this direction and the magnetic field is in this direction. So, this is your current I and this is the magnetic field B, and then this I cross whatever IL cross B you do and get the thing. Now, consider the cycle, consider the part of the cycle in which the coil is this, the current is going this way, current is still going this way. So, that means if this is the thing, here I am in this region, and here I am in this region. So, the direction of current is not changed, current is positive here, current is positive here. So, this is corresponding to this picture, this is corresponding to this picture. So, the direction of the current is same, direction of the magnetic field is same. The ring is here, dB dt is now negative. The current is going down, the magnitude of B is decreasing, although the direction is same. So, dB dt is negative, flux is decreasing. This is anti-clockwise as seen from the top. What should be the direction of current here? Anti-clockwise. So, this is anti-clockwise. Since B does not change direction, but I has changed direction, this was clockwise. So, I should put an arrow opposite. No, yeah, here, yeah, this will be clockwise. Oh, that was correct. Initial arrow was correct. So, B has not changed direction, I has changed direction. So, the force has changed direction. So, in this cycle and in this cycle the forces are opposite, in this cycle and in this cycle forces are opposite, this cycle forces are opposite. So, consistently it is repelling, attracting, repelling, attracting, repelling, attracting. So, average force is 0, but gravity is always there, mg is always there. It is paramagnetic, it is aluminum, but you can do it with copper. Copper is diamagnetic, aluminum is paramagnetic. Our ring is aluminum ring. Okay, our ring is aluminum, which is but that does not play much of a role, right? Unless it is ferromagnetic, that does not play a role. The force is because of that I L cross B. That is why it should fall down. If it is switching too fast, that is why the average should be 0. If it is switching slow, then you should see some kind of going up and down, up and down.
Before it also gets Sir, applicable to IL force B, ये forces is the force of a magnetic field induction due to an wire flowing current I and length L on some other length elements. And current in this element is not changing, sir.
Which element?
Direction is not changing, sir. In the coil, sir.
Direction of?
Current is not changing, sir.
In these two cases, yeah, in these cases, yes. If I consider this part and this part, it does not change, I does not change, yes.
Direction of force will be always in vertically forward direction, sir.
No, I am looking at the force on the ring, on the ring. So, current in the ring and the magnetic field present there, they are to be considered.
Sir, this is a bias source, sir.
This is, okay, Biot-Savart law, yes.
Force on any length element due to the current flowing in this length, sir, will be this, sir. And direction of this will be totally determined by the direction of the length.
That is fine. So, here is that element, here is that element of the current, right, here is the element and here is the magnetic field. So, the direction will be determined by these two. Of course, it is this component which works, is that clear? It is not the vertical component of magnetic field that works, it is the horizontal component of magnetic field that works. Your fields are diverging. Okay. So, it is this component, this particular component that works. So, your field is like this and the current is like this, and therefore, you have a vertical force. In a perfectly uniform field, can you have a current? Can you have a force? If your ring is put in a vertical magnetic field, uniform vertical magnetic field, there won't be any force. The force is because of the inhomogeneous magnetic field. And therefore, it is this component, horizontal component radially outward or axially outward, that works. So think on this. I will leave it to you to think on this, why it is in equilibrium, what we are missing, where are we going wrong, something is wrong somewhere. दूसरा रिंग भी है क्या पतला, एक ही रिंग है, ऑल राइट. सो थिंक, हाँ, यस, here insulated material, okay, the effect will be much less, right, the effect will be much less. The only use of this this core is the following. If you have this coil and no core, your magnetic field will immediately turn like this. Very small amount of magnetic field will be here, most of your magnetic field will be here. When we put the core, stuff the core, and the core is extending like this, then your magnetic field is going up and then coming down. So only small amount of magnetic field will be in this region, large amount of magnetic field will be in this region. So the magnetic field is dragged up. The magnetic field is dragged up, and since our phenomena are all beyond the coil, whatever phenomena I see, I need some strong magnetic field in this direction. Of course, diverging, non-inhomogeneous, all those things, but in this direction. So if you don't put this core and put some PVC pipe and then put the ring and then switch it on, you will probably see a small, very small lift. That is the only difference. Okay? There is something missing which you have studied in your class 12. Yeah, all this is eddy current.
Sir,
Eddy current in the rods.
yes, sir, in these rows.
Uh,
When the amount of magnetic flux linked to this changes, sir, then the equivalent amount of magnetic flux linked to the coil changes. Electrical will induce in that, sir. And that's magnetic flux will oppose the motion of, will oppose the electric field, magnetic field of that side. But the eddy current is still in the
okay, good. So one proposal is that we are talking in terms of the current in the primary coil, magnetic field due to the primary coil. There could be currents in this core also. That core can also produce magnetic fields, and those magnetic fields can play the role which we are not taking into account. Whatever. Now, my first reaction would be that when you put a ferromagnetic core, just as I have made the picture, this extra stronger magnetic field that is coming is because of that current in the core only. It could be a real current, or it could be what you call bound current, but whatever. But at the end of the day, the total magnetic field is enhanced by a few tens of thousands of times, but the direction remains the same. If you put a ferromagnetic material in some magnetic field, that itself gets magnetized and produces its own magnetic field, which is added to the primary magnetic field, but the direction of the magnetic field remains still the same. It is only the magnitude that blows up, right. So, that will only add to the magnitude of the effect. Qualitatively, there will not be any this direction of that. I am applying the Lenz law only. Why it is saying? I am applying the Lenz law only. When I say that in this case, the current should be in the same direction, right? The current should be in the same direction. Okay, same direction, no, opposite direction, right, opposite. If this is going this way, this should come this way, and in this case, it should be in the same direction. I am applying length law only. Since your flux is decreasing, dB dt is negative, you are in this region. Direction is same. See, in this cycle, current is positive. So, current is increasing in magnitude. But the direction here up till here remains the same. No, this corresponds to this and this corresponds to this. This I is for the primary. This diagram that I have made is for this coil. वो वही चीज सारा चीज एक ही है, वो only the words are different. Only the words are different. This curve that I have made is for the primary current which is causing this induced current. So this is same in these two halves. Here the current is same direction, here the current is same direction in this one. So I am putting an arrow here and I am also putting an arrow here. Acha, okay. Okay. So if it is anti-clockwise, I should put it this way, and it's increasing, so it should be clockwise, so I should put it this way. And here I should put it this way, and this one is now in the same direction. So this will be going like this. Okay. But still the problem remains the same. The problem remains the same. Half the time these two are in the opposite direction repelling mode, and half the time they are in the attracting mode. So that averages out to 0. Alright, so let's break for the lunch and think on this. We still have one more day to discuss. Chalo.